Hello everyone, I'm improving my device, hope that will have a better resolution for my videoing. In the last lecture, we talked about the penalty, the L2 penalty or the L1 penalty. Let's take the L2 penalty as the example, which says my loss of W is my good old square loss plus some penalty of the weights, okay, the L2 norm of the weights per square. And maybe you can also put a half here, it doesn't matter. Okay, it doesn't matter, so let's put it here. So in this lecture, we're going to interpret this loss as with some probability interpretations. And in particular, we're going to show that this is known as maximum posteriori, or known as MAP estimation. Okay. So let's remind ourselves for the maximal likelihood estimation. So this is different from maximal likelihood estimation. So let's talk about maximal likelihood estimation first. Which is known as MLD. The assumption for MLD is suppose my data is indeed generated by a function which is known as the linear function W transpose X plus epsilon. It's my target, okay, where epsilon is sampled from a zero mean with standard deviation of the variance. I call it sigma square, okay? I call it sigma epsilon square. This is my assumption. And for MLE, my estimate of MLE hat is argmax over data parameterized by W, okay? So it's my MLD estimation. So here, I wouldn't say it's a conditional bar, although the meaning is similar, okay? It just means given W or with W being fixed, okay? What is the probability of D? But when we write a conditional bar, it says W is a random variable. But if I write W as the semicolon, then I say it's a parameter, okay? In both cases, it says it's given. But if you write like this, W is not a random variable, okay? I don't have any distribution on W. W is a fixed constant. Although I don't know it, I would like to estimate it, and here's my estimate, okay? So this is the maximal likelihood estimation. So now let's go back to the max posteriori estimation. So now I have the same assumption. So I still have this, okay? I still have the, still have the assumption of my data. My target is generated by a linear or fine transformation plus some noise, which is Gaussian noise, okay? Then I also assume, we also assume there is a prior distribution W, which is PW, okay? It's the prior distribution. So this is a little bit difficult to understand. What does it mean by a prior distribution, okay? From a frequentist point of view, a distribution is set in terms of a random variable, which is the outcome of a repeatable experiment. And the probability is that if you try the experiment forever, what is the average outcome, okay? It's either 1 or 0, then you take the probability, okay? You take the average, it gives you the probability. But here is W a repeatable experiment. So now I assume the data is generated by this. So I can repeatedly generate data, okay? But can we even repeatedly generate W? It's a question. So it says, I will restart my universe, I will restart my world, and let's try another W. So it doesn't seem to be possible in the frequent interpretation. So that's why we need to have a Bayesian interpretation. So just let's remind ourselves again. So for a Bayesian interpretation, so there are a lot of Bayesian or Bayes stuff, okay? Be careful what does mean by Bayesian. So in here, Bayesian interpretation of probabilities just says for any random variable, unknown, then it's a random variable. For anything unknown, if I don't know it, it's just a random variable. Anything unknown, it's just the random variable. And the probability of the random variable is our subjective belief. Okay, it's subjective for no reasons, but some people are, have a good intuition, then they have a better machine learning model. Some people has a worse intuition, then their machine learning model is worse, okay? So it's subjective belief. Then in this way, I can reasonably interpret what does it mean, okay, by P of W. It just says, I don't know W. Then I have a distribution over W, okay? Then the question is, how can I determine P of W, okay? So is it going to be a Gaussian, or is it going to be some other distribution like uniform over a range or whatever? The way of determining the prior distribution is a little bit tricky. One thing is you can look for previous experiments, okay, different tasks, and you take the average, you say, this is my prior distribution. But sometimes it's not a good approach either. And because after you count something, you may have a non-analytic function, or you may get a function like, you may get a distribution like this. You cannot represent it by a Gaussian distribution or by some other distributions, okay? It may not have the analytic form. So still you want to have a good format. And in this case, we're going to assume the W, the prior distribution, is a Gaussian. Okay. So you see the reason? It has a good format. Okay. First, it's analytic. You can express it by a formula. But if you talk about a generic distribution, you look for all previous machine learning tasks and you get the distribution. It may not be a parametric form. Okay. So that's why we decided to go with the Gaussian for this case, for the linear regression problem. And we will talk what is a convenient prior in general. And the next thing is what is the average of W? So what is the mean? So I decided to say my mean is 0, okay? Because for linear regression, some feature may be positive, some feature may be negative, and we don't know whether the feature is negative or positive, or we don't know whether the feature is negatively correlated to the task or positively correlated to the task. So we don't know about that. So why not let's just assume the W without any information about your data, the prior is Gaussian, 0 mean, and standard deviation, I call it sigma W square. Okay. So does it make sense? So I say without knowing data, I don't know W either, right? So I just assume a prior distribution over W. I have the right to assume that. I have the right to define my subjective belief. And now my subjective belief is this, okay, with some hyperparameter sigma W squared. Okay. Then the principle for max a posteriori inference is we would like to choose WMAP hat as the argmax. Okay, of course it's maximum, so it's argmax over something. But definitely you can say it's the negative log likelihood. Then it gives you the argmean. Okay. Anyway, so let's talk about argmax over the posterior distribution. So it's a posteriori, which means the posterior distribution of my W. Okay. Okay. Sorry. Posterior. Okay. Does it make sense? Now I model W as a random variable and it has some prior. And suppose I can compute the posterior. Then I say, given this data set, what is the most likely W that I can have? And then I choose that W. okay? It's different from the maximalized estimation. The maximalized estimation says W is not a random variable. You cannot model P of W. And then given any W, you will have a distribution. You will have a probability of your training data, okay? Then you will tune such W to make the probability of your training data maximum. But the maximal posteriori estimate says, my training data is fixed, so I don't care about my training data. I only care about my W, right? I only care about the probability of my W, and I will choose such W that is most likely with this observation, okay, with this training data. So this is the philosophy of maximalized estimation, okay? So you see here, you can think of it as WPD given W is the same thing. I mean, in here, you treat W as a probability distribution, but you don't care about the probability. But if you write semicolon, you say it's not a random variable. Okay. But the maximalized estimation says, I don't care about data. Data is given. Why do I need to model the probability of data? Data is just this, okay? But now I consider what is the probability of my weights, okay? Under this data with this prior, then I choose the most likely weights. Okay. With this thing, then I could say, so we need some factorization, okay? So I can say this is P of W, P of D given W times P of W, right? Usually we write in the other way around. Okay. So this term says what is the prior for my W? If you don't have the prior distribution for W, you cannot compute the posterior. Okay, you have no assumption on W, then even if you observe some data, you have no posterior. That is the frequency analysis, or that is the maximalized estimation. But here, I have a prior over the W, and then I can compute the likelihood. Okay, this is the same as MOD. Then if you divide it by the probability of your data, then it works out. Then it's just the Bayes rule, right? So I can say this is the Bayes rule. Okay, is that clear? So basically the prior times the likelihood divided by the probability of data gives you the posterior, okay? So this is the same as saying max over W, P of W times P of W given P of D given W, okay? Because I can ignore P of D, okay? P of D is the probability of my data, but my data is fixed, so the probability is fixed. So you can say P of D is integrate over all kinds of P of WD, dW, then this is, I first have P of W, then given that W, I generate D, but I integrate out all kinds of W. Okay, so I should put it higher. So in this way, this W is different from my W here, right? Because it's an integration variable. And after you take the integrate, this variable is eliminated, right? So I can call it W star, or W star is, I just denote it as the integration variable. Then in P of D, it's not a variable of the W here. The W here is the variable that you would like to optimize, okay? So P of W is not a function of the optimization variable, then it has no effect in the argmax, right? In the maximization or minimization, if you multiply by a positive constant, it has no effect, and P of W is definitely positive, so no effect. I just eliminate the denominator. So I can also write like P of D P of W given D is the same as P of W times P of D given W divided by P of D, which is proportional to P of W times P of D given W. By proportional, I just say this is proportional in terms of W, okay? So I can say this is my W. And this is my P of W times P of D over W, okay? And by saying proportional, it just means there is a true probability. So this may be, let me draw it here. This may be my P of W given D, okay? So this is the left-hand side, and this is my right-hand side, okay? By saying proportional just means for different W's, okay, what you get from the left-hand side differs from what you get from the right-hand side by a multiplicative constant, okay? And in particular, the constant is 1 over PD, okay? This is the meaning by proportional in W. I mean, if you go this, you still get this. You still get this line, right? So I can say PD is a constant in terms of W, okay? So when you consider different W's, PD does not change. But when you consider different data sets, PD changes. But for the max a posteriori estimation, we assume the W is given, okay? So now we need to plug in what does it mean by P of W and what does it mean by P of D given W, okay? So I mentioned P of W is a, so W is a vector. For every element, it's independent, okay? So now I can say this is the product, okay, over different particular W, I is from 1 to D, okay? Suppose it's D-dimensional times this is what we know, right? So this term is what we know. So this is from data sample 1 to M, P of Tm given Xm parameterized by W. And this time it's given X and also W because I model W as the random variable. Okay, so this gives me argmax W. Okay, I just need to plug in this term. And by the way, I can take the log first, okay? It gives me neater expressions. So this is I from 1 to D log P of Wi plus sum over M from 1 to M log of probability Tm given Xm and W, okay? Then what I need to do, I need more space, so I write it here. This term is I just write it out. So the probability is a constant like 2 pi sigma W, right? So the standard deviation, I assume for every Wi, the standard deviation is sigma W and it's zero mean. So it's exp sigma W squared okay, Wi minus mean, which is 0, square, plus so this time I know the T is sampled, it's contained by the epsilon, and its variance is sigma epsilon, okay? exp then Tm minus W transpose. So this Wi is just an element of the vector W, right? So Xm squared. Okay, it looks scary, but there's nothing complicated here. Then I can say argmax. Okay, so I guess we are already familiar with some of the constants, so we can drop some constants. You see, if I drop this term, it has no effect because there's nothing to be optimized, and it gives you a constant, right? So it gives you a log A times B is just the log 1 over plus log 1 over this, right? And likewise, if I remove this term, it gives me this term, right? And it gives me the additive constant, and we are optimizing over W, but here we don't have W. Sigma W, I just denote the variance of sigma. It's a constant, it's not a function of W, okay? So here I don't have any W, so I can just drop these two terms. So I just drop the green term, the green factor, and then we see the log and exponential, so we can cancel it out. Okay, now it looks something familiar. So I would say, okay, I can put my summation immediately before my weights, okay? Because this term is a constant, so I can move it out of my summation, right? So I just arrange the terms like this, plus. Okay, so now it's pretty clear. So I say this is argmin, then I cancel I change the minus to plus, okay? So it gives me 2 sigma epsilon square from 1 to m Tm minus W transpose Xm plus. So I cancel the minus W square this. Okay, and then I can rearrange the term. I say this is M, okay? So you see, I divide the entire term by M, okay? And I multiply it by epsilon square, sigma epsilon square. And here we have the sigma omega square too, okay? And we know this term is the norm of W square, L2 norm of W square, right? So I can just write the term here. Okay. So now you see everything here, it's a constant, okay? I don't know what is epsilon, sigma epsilon, I don't know what is sigma weight, but when you divide the two variants, I don't know it either. And then you multiply it by 1 over 2m, I don't know the term either, right? So I can rebrand this term as lambda. So this is equivalent to L2 penalty for MOD, right? Because it's the L2 norm, and then this is the MOD, okay? Here we observe that how your prior for your weights really affects the strength of your L2 penalty, right? So suppose sigma square is very large, which means your prior, is very widespreading, okay? I say I have no preference about my prior, okay? And the weight can be reasonable within a very large range, then, you know, if the sigma W is large, then the lambda is small, okay? Right? And vice versa. Right? And the lambda small just means I have a less penalty, because your prior says every W is fine, then I have no penalty, I have no constraint, okay? Then the C is large. You remember the soft penalty is equivalent to C, the hard constraint, okay? Then the C is large, right? Because your lambda is small, you have no penalty, then your feasible set is larger and the C is large. And in this case, it's more likely to be overfitting. Okay, because you have a less penalty, you have no prior information, and you have a relaxed constraint. Your constraint is very mild and more likely and less likely to be underfitting. On the other hand, if I have lambda epsilon is small, sorry, sigma epsilon is small, we have the lambda is large, because in this case, your prior is very strict, okay? So this is your prior. It says, I know epsilon must be around 0 with a very large probability. After you observe the data, the posterior probability that the weight is very far away from 0 is still small. And then it means you have a large penalty. You want your weight to be smaller and smaller. So it's the lambda being large. And if lambda is large, your constraint that the norm of W is less than C, with this C would be small. Okay, and it's the vice versa. So I don't have to write it, but I can rearrange my writing, right? So this time it's more likely to be underfitting because your learned weights will not depart from 0 too much, okay? And then you have a very large penalty that you care more about the norm of the weights. And it's equivalent to say, I'm restricting the feasible set to a very small plate, to a very small circle, okay? So we also notice that if your likelihood is a Gaussian, so here, if your likelihood is a Gaussian, sorry, here, so I use another color, red. If your likelihood is a Gaussian, and if your prior is also a Gaussian, then the prior times likelihood, or the posterior, okay? So this is a constant, so I can ignore that. But the posterior, P of W given D, is also a Gaussian. You see that? You see that? Because you know, the P of W is a quadratic decay, right? Some constant quadratic decay, right? And P of data given W is some other constant, also quadratic decay. And when you multiply these two terms, the exponential gives you something minus something like this, right? And you also have some constant K1 times K2, but it doesn't matter. Eventually it will be proportional to that. Then it's also quadratic decay, right? This shows a Gaussian multiplied by a Gaussian is still a Gaussian. Then it gives you the posterior, also a Gaussian. So your prior is a Gaussian. After you multiply the Gaussian likelihood, you get a Gaussian posterior. So in this case, it's known as the conjugate prior. Conjugate prior just means the prior and posterior distributions have the same format, but usually with different parameters. this is not included in what does it mean by the conjugate pri, but in the usual case, the parameters will not be the same, but they must look the same format. And then, the computation becomes very convenient, right? So you have some prior, and then you observe some data, you get the posterior. If you observe more data, then the first posterior becomes the prior, and then you can continue learning, right? So we will talk about this in the basic learning part. But let's just get familiar with this terminology. Conjugate prior just means your prior and posterior have the same format. And there's no mathematical reason, no scientific reason to choose conjugate prior. Okay, it didn't say my likelihood is Gaussian, then my prior distribution of my weights is more likely to be a Gaussian. It's actually subjective. You believe it's Gaussian, then it's Gaussian. You believe it's uniform, then it's uniform, okay? So there's no scientific reason why it has to be conjugate. You have to choose the conjugate prior, but it's more mathematically convenient. The main reason that you choose the conjugate prior is it's more mathematically convenient. And especially sometimes you have constraints, and then if you have the conjugate prior, it's usually automatically satisfied, okay? So this is the reason why we choose the prior, the P of W as Gaussian. First it look nice, then I choose it, okay? And also it's conjugate prior, and it's very mathematically convenient, okay? It's just look the same, and then you just pick another parameter. It's just penalized by the norm. Okay, so this gives us the max a posteriori estimation. Our next goal will be how can I tune the lambda? Okay, how can I tune my sigma? How can I tune my lambda or C? So you only need to tune one, okay? After you tune one, the others are fixed. Or we have other components. For example, the learning rate. How can I tune the learning rate or the step size? So there are many hyperparameters. So this will be our next goal. We see in machine learning systems, there are usually a lot of things to tune. For example, here we have the lambda, okay, or sigma or C. There's some correspondence, but usually we tune the lambda because it's the O2 penalty, and lambda is the coefficient of the penalty. And there are some other things. For example, you have the learning rate. If your learning rate is too small, then you are walking tiny baby steps, and it takes too much time to reach to the optimum. And maybe your learning rate is too large, then you are overshooting, right? Or maybe you are doing learning rate decay. If your learning rate decay is too small, maybe your convergence is not very good, or your decay is too fast, then you don't have enough energy to go to the optimum, okay? So in machine learning systems, usually we have a lot of things to tune, and these are my design choices. So the question is how to tune these things, okay? They are known as the hyperparameters. For example, lambda or the learning rate or other things. So the hyperparameter is some tunable parameters not optimized by the machine learning model, okay, not optimized by the machine learning system. Just like you remember, our machine learning system is to look for hypotheses, that is argued mean hypothesis from the hypothesis class, which is H, okay, with my training data. But maybe this J is subject to some other things, for example, lambda, okay? It's a hyperparameter. It's not tuned with this optimization process. And it's not a parameterization of H, but it's still something affects your hypothesis, okay? These are known as a hyperparameter. So the methodology of tuning a hyperparameter is try it and see whether it works well. So the basic idea is to try different values of, maybe I just call it lambda, okay? I just call it lambda here. Try different values of my hyperparameter and choose the best. It's the very naive idea, right? So I have the first attempt. So what if I say my algorithm is like this? 4 different lambda, okay, values. I train my h, okay, which is arg mean over h j lambda of h, right? Test such h on my unseen data. This is my training data. This is my unseen data, okay? So I try different things and return the best h, okay, gives the best performance. On GD unseen. Okay, this is my first attempt. Is it a good experimental protocol, or is there any obvious issue with this algorithm? So I can see some issue, for example, issues, problems with this attempt. So I just, I just have a random prediction. So my h is purely random or pseudo-random controlled by lambda. Okay, or it's just random. I can just say h is a random hypothesis. And the lambda is dummy, okay? You try different things and it's dummy, it has no effect in h. Every time you get a new h and you just have some random predictions. Then as long as you try many, many times, at some point we'll be lucky enough. And you say, okay, this h is really good. And I return this h, okay? But actually it's nonsense. It's no better than any other h. It's not learning anything. It's just luckier on this unseen data, right? And for some other data, for example, if you deploy it in the stock market, it may not be so good, right? So this is the example that, maybe you are choosing the best h by chance, and then you believe the model is very good, but in fact it's not. Another issue is, for example, we say we are learning machine learning, so we're doing human learning, okay? So I have some hyperparameters. So h is my brain, okay? It's my brain. So I have some hyperparameters, for example, how many hours do I spend on this course, okay? Maybe I spent 1 hour every week. Maybe I spend 10 hours every week for this course. And I would like to apply my brain, I would apply my hypothesis to the exam, okay? And then I will try different hyperparameters, which is maybe I learn it for 1 hour, learn this course for 1 hour, learn the course for 5 hours, 10 hours, so on and so forth, right? Then what's wrong? You see, if you try to learn machine learning course by 1 hour and you try to apply what you have learned on my exam, then if you don't feel you are doing well in the exam, you lose the chance to go to the for loop. It's not rehearsal, it's not drill, so you lose the chance to try it again. So the other is the unseen may only be accessible once, okay? So the first issue is maybe better estimated the performance is better estimated just by luck, okay? And the other issue is the unseen can only be accessed once sometimes, and oftentimes, just like you go to the stock market and I would see whether my machine learning model to predict the stock price is good or not. If you lose some money, okay, then you're done. You know, you cannot get the money back, you're done. So it can only be accessed once. So that's why a very important idea is in machine learning is try to do some rehearsal or some drill before deployment. Okay. Or you can say do some internal validation. Before I apply my machine learning model to predict the stock price, before I apply it, I try to validate it internally. I don't apply it. I don't direct it by the next stock, okay, based on my machine learning model. I just do some practice and see whether it works well. After a few days, I feel my model is good enough. Then I buy the real stock, okay? So it's the internal validation. So what can we do? So suppose, consider a supervised learning task. We are given a label data, right? A label data. So this is my D-train, but now I call it D-labeled, okay? It's M, T, M, okay? For some M's, okay? So it's a set of pairs of input and output, right? So since I would like to do some rehearsal, then I can split my D label into two parts, okay? One is the D train, and the other is the D test. We call it D validation, okay, validation. And some people call it D cross validation, it's the same. But some people also use cross validation to refer to k-fold cross validation. I will touch it later, but let's just use the name validation to avoid confusion. And then you can do internal validation many times, okay? As many times as you like, until you get the best edge, then you deploy it, okay? So you still have the D unseen. The algorithm becomes, this is my second attempt. The algorithm becomes for still different lambdas, okay, for different lambda values. Train edge such that it's the argmin over edge from my hypothesis class, J of different lambdas, okay, H and D train. So I split my labeled dataset into two parts. One is still called D train. The other is called D validation. Okay. Then we do validate edge by the error. Okay, this is the measure of success of such edge on my validation set. Okay. Then now I return edge with the best measure of success, which means with the lowest error, okay, measure of success. And then apply edge to the unseen. Okay, so you see this algorithm is very similar to here, but you avoid using the unseen for many times. The unseen is only reserved once, okay? You know, if you believe the validation is not so good, the measure of success is not so good, you can try different lambdas, or you can even tune your J or tune your hypothesis class edge, okay? You can try everything until you are satisfied. then you apply it. And you also know that the performance on the D on scene is real, right? But in here, if you pick the best edge on D on scene for many times, then the performance of edge on D on scene is inflated because of the luck. And also, sometimes D on scene can only be accessed once, and then you cannot apply this algorithm. In the second round, you would like to apply to D on scene, it gives you a runtime errors and no access, okay? So this is wrong. This is a very bad practice of machine learning. And some people do it in machine learning papers or machine learning application papers, but this is no good. And this is known as the D-test. Okay, so my unseen data, so now I call it D-test. And my label data, which was used to train my model, is now split into two parts. One is the D-train, on which I train my data, and the other is the D-validation, on which I tune my hyperparameters. Okay, so by the way, in industrial applications, this step may be a real deployment of edge, right? So you say, I have some applications and I validate it very well, and then I deploy it, okay? I deploy the best, so, I have no other choice. Even if it's by luck, I only have this model, this is my best choice, then I deploy it. Or sometimes you want to have an estimate, then you still apply it, right? So this is the industrial application. So if you have the application, then you deploy edge, okay, to earn your money, to do a business, okay? And sometimes you don't care too much about whether you have a good estimate or not, okay? Even if my estimate of the performance is not so good, I have no choice. I can only deploy this model, the best model that I believe. But in research, so this is machine learning application or industrial application. But in machine learning or machine learning application research, things are a little bit different. So machine learning research. So, research is usually not, how much money I can earn. It's not about whether I deploy the system or not. The research is usually you are advancing the human knowledge, okay? I develop a new machine learning system. Or nobody can solve this task before, but when I apply some machine learning system, I can solve it with a reasonable estimate of the performance. So in this case, you are actually mimicking the scenario of deployment of a machine learning system. You don't have to deploy it, right? You just do it in your lab and then you publish a paper. So it's not a deployment. So in research, you don't have this, but you must have this, okay? So this is my test, by the way. Okay. And in research, you don't actually have unseen data. You have the whole data set, right? You have the whole data set. And you pretend that I'm not sure about the labels for some part of my data and use it as the test. And I train on the training set, validate on the validation set, and test it on the test set. Is that clear? So in industry, maybe you also care about a good estimate of the performance that you do it. If you don't care about that, you can directly apply your machine learning model to unseen data. In research, everything is offline. I don't have unseen data. I don't interact with the real clients, okay? So I'm just doing paperwork. So in this time, my label data set actually is split into 3 parts, okay? D-train, D-val, and D-test. Okay. 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 Then you have some iteration. So you still apply the algorithm. It's the same as here, right? Still you apply the algorithm training validation many times until you are satisfied. You pick the best model. You pick the best model and you apply it to D-test and report it in paper. Okay. report error of HD test on paper. And this rules out the noise, okay? So if you pick the best edge on D-val only by luck, then the performance on D-test will not be so good because the noise is usually independent. And then if you try it again, you don't have that luck. So in research, this is my D label, okay? In application, you can have this, or you can omit that. You just directly apply it to the real task you deploy your machine learning system. Okay. So this step mimics the deployment. Okay. So here's the question. How can I split D-train and D-val? Okay. Or in research, sometimes you also have the right to choose D-test, okay? So definitely I want D-train to be large. Right? If I have a large data set, usually my model is unlikely to be overfitting, right? If I have only 3 samples, then of course I can remember all the samples. I'm not learning the true pattern of my data. If you have thousands of samples, then I have to learn something intrinsic to the data. If I just remember the data samples, my model does not have that capacity to memorize all the things, okay? So I want my D train to be large. I also want my D-val to be large. Okay. Because if you have a large validation set, then this part usually gives you a better estimate of your hypothesis, right? You have a better estimate. You have a low variance in evaluating your hypothesis. You also want the test to be large. Then it's a contradiction because the total budget you have is a fixed D label, and you want to split into a few parts, and you want each of them to be large. So here is some common practice. If in previous research papers, if there is a standard split exists, follow it, okay? So if people have already separated the data set into 3 parts, and then a few papers have already followed that split, then you also follow it. If it doesn't, the standard split doesn't exist, you think of what is your data size, okay? So for example, maybe you have like 100 samples or 1,000 samples, the rule of the thumb is maybe, for example, 6 by 2 by 2, okay? 60% goes to training, 20% goes to validation, or 20% goes to test, okay? There's no particular reason, but it's just a common practice for medium sized, okay? But for large sized, then usually you will have a smaller percentage for validation tests. For example, you have 10,000, okay, or even 100,000 samples for validation and test, okay? But you have the remaining for training set, okay? For example, you have the maybe 1 million samples or even 100 million of samples, okay? So you don't have to increase your validation and test set proportional to the whole label data set you have. And the reason is because the variance of a few IED random variables is 1 over the number of samples times the variance of each of the random variables, right? So the variance decreases, the variance of the evaluation decreases with the validation size or the test size increases. It's not affected by the ratio of your training and validation set is, okay? So good enough. And usually your validation set is even smaller. For example, it's even smaller, okay? Smaller than size of your validation, smaller than the size of your test. Okay, for example, you have 100,000 samples for test, but you only have 10,000 samples for validation. And the reason is validation is done many, many times. If you have a very large data set for very large validation set, then it may be very slow. Okay, so this is the large sized data set, medium size. And the tricky thing is, what if I have a very small sized data set, okay? So maybe a few samples, or maybe 50 samples. In this way, if you separate by 6 by 2, 2, then the training set may not be good enough to well train your model, but the validation set may not be good enough to have a stable evaluation. So in this case, we typically do k-fold cross-validation. So what I suggest, I mean, different people have different protocols, but what I suggest is you put your d-test intact, okay? D-test is always to mimic a real deployment. If it went wrong, then the life went wrong. But what you can actually do is you don't train your model once on a fixed subset of the training or validation set, but you can try different subset of your training and validation, and then you train on a part of your train validation part and evaluate on the other part, and you try it many times and take the average, right? So k-fold validation just means I separate my original d-train and d-val into k-folds, okay, into k-folds. And my training algorithm becomes, I still have different lambda values. Okay. And I try different k-folds, okay? I try for little k equals 1 up to capital K. So I call this capital K, okay, k-folds, but it doesn't matter, right? So now I have my, I call the entire set maybe D label. I call this set as D label. Okay. Or maybe I call this set D train. I mean, it doesn't mind how I call it. Okay. And now I say this is D1 up to DK, right? So you see D train is the union of little k from 1 to k, dk, right? And they're disjoint subsets. Train my model. Okay, h in my h by j of lambda h, okay, d train except dk, okay? So first I train my model on this part and I evaluate it on D1. Second, I train it on D1 plus D3 up to dk and I evaluate it on D2, okay? Third, I train on D1, D2 plus D4 up to dk and evaluate it on D3, okay? Validate my h by okay. So after you have done 1 to k, consider the average loss, okay, for this lambda, and the average error for this lambda, which is the 1 over k, sum over little k to k, the error of h you find, you know, for the kth error, right? So for the kth hypothesis. Okay. So this is for here. Okay. Then return the best h, okay, such that yields the best, oh sorry. So first, here I don't have a single h because the h is a function of k. For different k, I have the single. So, but now I return the best lambda. So this is my best hyperparameter, okay? And I haven't got a particular h yet. But you remember in machine learning model, obviously the most important thing is prediction. And for prediction, you must have a model. So why not, let's say, mix. So you have different design choices, okay? So I can say mix D1 up to DK again and retrain my model. Retrain my model, H is on the D train, okay? On the entire data set, I just mix them once again with this particular lambda, okay? Lambda star, with this particular lambda, I just retrain again on the entire data set, and then I return H. So this is one possibility. The other possibility is, alternatively, you can just return H1 up to HK, and then your prediction is the average of H1 up to HK with that best lambda. It's also possible. I mean, you have different design choices. Machine learning, you know, we do have some math part, but we also have some design choices. It's also possible, right? And every time you make a prediction, you just take the average of the prediction, okay, for regression problems. But for classification problems, you can do a voting, right? It's also possible. But, you know, this is known as the k-fold cross-validation, okay? But what I would say, k-fold is almost obsolete in real AI problems for a few reasons. First, you have non-convex optimization. Maybe, you know, you may have non-convex problems. If you have non-convex problems, you have a issue, you know, every time you may not get to the same outcome. Sometimes you are here, sometimes you are here, okay? So maybe when you remix all the data and you try it again, you are very unlucky, you get here. You're not so good, right? So for non-convex problem, you cannot make sure that your hypothesis is the best, even if you have picked the best lambda, okay? It depends on your initialization. But for convex optimization, it doesn't matter too much. It's guaranteed that the more data you have, then the less error you'll make on unseen data. And the other reason is in AI, the recent advance of AI is largely due to the increase of computation power and the increase of data set. Okay, so now the data set is not a real problem. You know, if you really want to solve a task, you can ask humans to annotate data, right? And sometimes it's also important to do like few shot learning. Just means you really just have a few samples, okay? Or you even don't have a sample, still want to solve the task, unsupervised learning. And I've done a lot of things like unsupervised reasoning, or maybe unsupervised text generation. But still, people, not me, I mean other researchers, have enough budget to construct a data set large enough for validation tests, okay? I imagine that I'm in the low resource case and I do unsupervised learning or weakly supervised learning, but eventually we do have the data set for testing, okay? This mimics in industrial applications. For example, you have a new project or you're a startup, you don't have the resources, you can do it. But we still have, as a researcher, we still have a large enough data set for testing. So I would say recent progress of AI is largely due to the increase of data set, okay? So it's almost obsolete. I don't think, for example, in the neural era, this is a good idea. The neural networks are usually non-convex optimization. And if you do this, you don't know eventually, or even if you pick the best lambda, you don't know if your learned neural network is good enough, okay? So I guess it's obsolete. But by the way, if K equals the size of your training data, this means for every DI, it's just one single data sample, then it's known as the leave out one cross validation or validation, okay? But anyway, they are just obsolete. We don't use it as often as like 10 years ago. Okay, very good. So we still have a hole here. How do I tune this? How do I try different lambdas? So if we consider a single lambda, so usually you can tune it by a line search. Usually you do it by multiplicative fashion. For example, try lambda from, okay, for example, 0.01, 0.03, 0.1, 0.31, so and so forth, and 0.03, no, 003, 0.001. Okay, you try a wide range of possible hyperparameters, and then usually you do it in a multiplicative fashion so that you can test a wide range. Okay, if you try it in an additive way, for example, I say 0.01, 0.02, 0.03, then maybe my best hyperparameter is 0.1, right? Then you need 1,000 experiments to get there, okay? So you usually do it in a multiplicative way. The other is, this is one thing. The other is use human insight, okay? For example, I know this is my mean square error. Don't even need this lambda, I mean. Anyway, lambda increases is underfitting, right? And lambda decreases means it's overfitting, likely to be more overfitting, okay? Then you can plot the curve, for example. This is the number of epoch, okay? You just train your model. And this is your error or your loss, okay? Then you can plot how your training loss and your measure of success, your error on the validation set goes along the epoch, okay? So maybe like this. So this is J on train. And this is the error for on the validation set, okay? Error on the validation set is not eval, okay? So if it's overfitting, if I believe this is overfitting, this means your training is optimized too well and your validation set, your validation performance has a large gap between your training performance, then you need to increase lambda. right? Because if you increase the lambda, it may be more likely to be underfitting and it may recover from overfitting, okay? If your loss or error look like this, okay? For example, your train is this, and your error is this. So this is the train, and this is the val. If you believe this is underfitting, just means you haven't learned too much about your training set. Okay, so I don't even remember the training samples. I don't even fit my training samples very well. Then you need to decrease lambda and making your model better fitting your training set. Okay. The next thing is, so this is one lambda. How about I have a few hyperparameters? Lambda 1 up to lambda maybe k, okay? So now enumeration is not possible. Suppose I have only 2 choices for lambda 1, and I have 2 choices for lambda 2, so on and so forth. And suppose maybe I have 10 hyperparameters, not large. Then all the possible configurations is 2 to the power of 10, okay? It's 1,000 configurations. It's impossible to try all of them because if you try one configuration, you need to train your model. And training a machine learning model is not fun. Sometimes it takes a few minutes, sometimes it takes a few days or even weeks, okay? It's not fun. So how can I do that? And the very common way is a common approach. It's known as grid search. Okay, this means for I from 1, call it k, little k, from 1 up to capital K, fix lambda 1 up to lambda k minus 1, lambda k plus 1 up to lambda capital K, and tune. Now all the things are fixed, okay? So you have lambda 1, lambda 2, okay? So you fix one thing, you fix one lambda, okay? So suppose this is my validation error, okay, on different lambdas. So you fix, suppose you are here, then you first fix maybe lambda 1. So you fix lambda 1, you are only here, and you tune the lambda k to the best. Now you get here, okay, you probably get here. To the best. Then you fix lambda 2, okay, lambda 2 is here, okay, so you fix lambda 2 and you tune your lambda 1 to the best, it's here, okay, so you start from here, this is your first lambda, this is your second lambda, this is your third lambda, okay, you move from here to here, and then you fix lambda 1 again, you tune lambda 2 again, you tune it to the best, okay, this may be your lambda 3, so and so forth, 4. So and so forth, you know, after a few updates, it gives you to the some reasonable hyperparameter, okay? It may not be best, and you may not even wait until the convergence, but it gives you some reasonable results. And you don't care too much about which is the lambda here, because the training of your machine learning model will compensate for some imperfect choice of lambdas, okay? But if the lambda is too bad, then of course it's bad. But if it's here, okay, reasonably good. So this is known as grid search. And sometimes you have some insight, or you know maybe lambda 1 and lambda 2 are correlated. Then, you know, if you do this, if you do grid search for only one lambda at a time, it may not be good. So maybe you can do grid search for 2 lambdas at a time, and you do an enumeration over 2 lambdas. So you fix all other things, all other lambda 3 until lambda k. You know lambda 1, lambda 2 may be correlated. So you draw lambda 1, you have a few values for lambda 1, like you have a few lambda values for lambda 2, okay? And maybe you draw a two-dimensional table, and maybe you try 3 or 4 values. It's like 10 to 20 configurations. It's not too bad, okay? So this is also sometimes useful, or if there could be lambdas highly correlated. Okay. Okay, so good. See you next lecture.